In this video, we're going to do some examples of using the matrix exponential to solve differential equations where the matrix is diagonalizable. We actually know how to solve this without using the matrix exponential, but I just want to explain why the matrix exponential gives you the same answer. So before we go into that, let me just make this comment. So suppose that you can write A, the matrix A, as P, C, P inverse for some matrix C and some matrix P. And the fact that you have a P inverse implies that P is invertible, right? So one of the facts about the matrix exponential is that e to the at is just P times e to the ct times P inverse. And the key fact about solving x prime equals ax is that the general solution is the span of the columns of e to the at. Okay, so the general solution to x prime equals ax is, well, when you have a matrix and you look at the span of the columns, now this matrix e to the at involves t, right? But it's still a matrix. So you can look at the columns, you can look at all linear combinations of the columns. So in linear algebra, what do you call the span of the columns of a matrix? It's the column space of the matrix. So the general solution to x prime equals ax is the column space of e to the at. Now there's a key fact. This is a useful thing to keep in mind because this actually shows that actually the general solution to x prime equals ax is also the column space of P e to the ct. So in other words, you take these first two matrices, you multiply them, and that matrix you get, the span of the columns of that matrix is the solution to x prime equals ax. So what I'm saying is that the column space of P times e to the ct is the same as the column space of e to the at. So in other words, so the reason is that the column space of e to the at is the same, is equal to the column space of P e to the ct. Now, why is that true? So that has to do with a linear algebra fact, which is that suppose you have two matrices. So you have a general linear algebra fact. If you have a matrix A, okay, and a matrix B, if B is invertible, then the column space of AB, I'll just write it col of AB, the column space, so it's the span of the columns of AB, is equal to the column space of A. If we just take that for granted, how do we get the result I was just mentioning? Because you can apply this to the case where A is P e to the ct and B is P inverse. Because remember, P inverse is invertible, right? It has an inverse of P. So you have this matrix P e to the ct, which is, let's call it A in this case, then if you multiply on the right by P inverse, that's an invertible matrix, that does not change. The resulting matrix, e to the at, has the same column space. Okay, let's think about why this is true. The reason this is true is because when you have a matrix A, so let's say its columns are V1 to Vn, right? And you multiply by a matrix B, what you're doing when you're multiplying on the right by a matrix is that you're taking linear combinations of the columns of A. So the columns, each column of A times B is a linear combination of the columns of A, because, right? Because if you take A and you multiply by the first column, say, the first column of B, okay, that's just going to be a linear combination of the columns of A. And if you take A times the second column of B, that's also a linear combination of the columns of A. So the first column of AB, well, that's A times the first column of B. That's a linear combination of columns of A. The second column of AB is just A times the second column of B. That is also a linear combination of the columns of A, etc. So the columns of AB are linear combinations of the columns of A. So if the columns of AB are linear combinations of the columns of A, then any linear combination of the columns of AB must be a linear combination of the columns of A. So for example, okay, let's say that A times B was like W1 to Wn, right? So each of the W's is a linear combination of the columns of A, so it's the combination of the VI's. So if you take something like 2W1 plus 3W2, right? If W1 and W2 are themselves combinations of the V's, then 2W1 plus 3W2 or whatever must also be a combination of the V's. So it's a combination of the columns of A. So, okay, so let's write that down. So any linear combination of the columns of AB is also a linear combination of the columns of A. Well, if any linear combination of the columns of AB, I mean, what is the word for the linear combinations of the columns of AB? That's the column space of AB, right? So the column space of AB must be a subset of the column space of A. Okay? So remember, the COL refers to the column space, not the columns, but the column space. So the column space of AB is a subset of the column space of A. But A can be written as AB times B inverse, right? And B inverse is an invertible matrix. So the column space of A, B, B inverse must be, by the same reasoning as what we had above, must be contained in the column space of AB. But A, B, B inverse is equal to A. So the column space of A is contained in the column space of AB. Well, if the column space of A is contained in the column space of AB, and the column space of AB is contained in the column space of A, then that implies that the column space of A is equal to the column space of AB. Okay. Maybe I should just explain this last part a bit more. So when the column space, you know that the column space, when you have a matrix times another matrix, times a second matrix B, and the second matrix is invertible, the column space of the product is contained in the column space of the first matrix. That's what this is saying. Then what I'm doing is I'm writing A as a matrix, AB, times another matrix, B inverse, which is invertible. So again, I've written A as a first matrix, AB, times a second matrix, B inverse, which is invertible. So applying the fact that I already found above, I know that the column space of that must be contained in the column space of the first matrix. So that explains how I got this equation, or this containment, that the column space of AB B inverse is contained in the column space of AB. I just applied the first fact that I already found above. And AB B inverse is just equal to A, so that gives me that the column space of A is contained in the column space of AB. Okay, so that explains why, so in general, when you have a matrix, okay, and you look at the column space, and you multiply that matrix on the right by an invertible matrix, the product has the same column space as the column space of the first matrix. So going back to this, okay, I have e to the at equals p e to the ct p inverse. So I'm thinking of my first matrix as p e to the ct. My second matrix is P inverse. P inverse is invertible. So therefore, the product has the same column space as the first matrix. So the span of e to the at, the span of the columns, of e to the at, is the span of the columns of P e to the ct. So that was a fairly maybe long-winded explanation, but basically it boils down to this linear algebra fact that I was trying to prove. Okay. So that explains why the matrix exponential gives you the same solutions as what we had before when you have a diagonalizable matrix. So for example, let's say that A is a 2 by 2 matrix and is diagonalizable. So it has two distinct eigenvalues, and this is a real matrix. So A is going to be of the form P dP inverse, right? And D is this diagonal matrix with eigenvalues lambda 1 and lambda 2. And P has columns which are eigenvectors with eigenvalues lambda 1 and lambda 2. So e to the at is just P times e to the lambda 1t, e to the lambda 2t times P inverse. And as we just explained, you can just multiply these two first vectors, PD. So that's going to be, this is e to the dt. So P e to the dt is going to be a matrix where the first column is e to the lambda 1t v1, and the second column is e to the lambda 2t v2. So if you take the span of these two columns, you get all vectors of the form c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. And this is exactly what we found before about solving the matrix equation x prime equals ax when you have a diagonalizable matrix. So all of this basically explains how that solution is tied into the matrix exponential. Okay, I just want to do one quick example just to illustrate. So suppose we wanted to solve this system of equations. x1 prime equals x1, x2 prime equals x1 plus 2x2, x3 prime equals x1. So first we write out the matrix differential equation. X prime equals this matrix, the first row is 1, 0, 0, second row is 1, 2, 0, third row is 1, 0, negative 1. So we call this matrix A. And this is a diagonal matrix, not diagonal, sorry, it's lower triangular. So we know that the eigenvalues are just the entries on the diagonal, 1, 2, and negative 1. And I'll just let you check that you can find eigenvalues. So let's say that that's lambda 1, let's say that's lambda 2, let's say that's lambda 3. And we can find corresponding eigenvectors v1, v2, and v3. So I'm assuming that you already know how to do this. I'm just going to write out, I'm not going to explain how to get this. I'm just going to write out the vectors you get. So those are my three vectors. And so my P is going to be this matrix, and my e to the dt is e to the t, e to the 2t, e to the minus t. So my general solution is x of t equals c1 times this vector times e to the t plus c2 times the second vector times e to the 2t plus the third vector, so c3 times the third vector times e to the minus t. And then let's say that I wanted to find, so notice that, by the way, this is equal to p e to the dt times c1, c2, c3. Okay, so suppose that we now have initial values. Suppose x1 of 0 equals 2, x2 of 0 equals 1, x3 of 0 equals negative 4. Well, as I explained before, we want p e to the dt times p inverse times this column vector 2, 1, negative 4. So we need this. And we could calculate P inverse, but for this it's actually easier to just use the general solution we found. So so let's write out what we have. We have x1 of t, yeah. And we just plug in 0, right? So if you plug in 0 in for t, you get x of 0 equals c1 times 2, negative 2, 1 plus c2 times 0, 1, 0 plus c3 times 0, 0, 1 equals 2, 1, negative 4, right? That's the vector, that's the initial value. And now we just need to solve for C1, C2, and C3. So if you write out the equations, Now, if you think about what this is saying, right, let's write this as a matrix vector equation. I'm just doing this just to illustrate the theory. So this left-hand side can be written as this matrix times this vector equals 2, 1, negative 4. Well, this matrix, okay, where have we seen that matrix? That's just the matrix P, right? So that's where this C1, C2, C3 is P inverse times 2, 1, negative 4. That is the constants that we want. But we don't need to, so this just goes back to what I was saying, that the general solution is P e to the dt times C1, C2, C3. And once we find the C1, C2, and C3 that work, I mean, we can find that by P inverse times 2, 1, negative 4, and then we just plug in those values, and that gives you the particular solution. That's the solution to the initial value problem. But we don't need to actually calculate the inverse because we can actually just solve this system by hand. Okay, because we have a nice matrix, right? I mean, this system is easy to solve. It's 2C1 equals 2, negative 2C1 plus C2 equals 1, and C1 plus C3 equals negative 4. So we have to solve this system. The first equation tells you that C1 is 1. The second equation tells you that C2 is 3. And the third equation tells you that C3... did I write down the right thing? Hold on. C3 is negative 5. I hope I wrote down the correct eigenvectors. Well, let's assume that the arithmetic is correct. So that gives me 1, 3, and negative 5. So then the solution is x1 of t equals 2e to the t. x2 of t is negative 2e to the t plus 3e to the minus 2t. And x3 of t is e to the t plus 5e to the minus t. So that would be the solution to the initial value problem. Let me just check my answer because it's not the same as what I got in my notes. Let's see. Yeah, I got C1 minus C3 in my notes, but hopefully this is correct because I don't see any mistakes here. So hopefully this is correct. But anyway, the point is that the method works. I don't think I made any arithmetic mistakes, but this is how you would solve a system of differential equations using the matrix exponential when your matrix is diagonalizable, and also how to handle it when you have an initial value problem.